Okay, so I lied in the last video. One more thing I want to talk about before we actually do an example. So I do want to talk about springs. So let's talk about how we deal with force in a spring. Okay, now, in this diagram I have a block here attached to a spring, and so here's a wall, let's say. So this is an immovable object, and so we've got this spring and it's attached to this block. And so this is when the spring is at its natural length, right? So this is called the equilibrium position, okay? So this is where we're going to set up our visual, because we want to set up the block, the origin, where the spring is at rest, okay? Also, in real life, if we had something set up like this, we would have to deal with friction. But for this, we're going to just assume that we have a frictionless surface, okay? So, if we move the block, if we pull the block this way, then the spring is going to get stretched, and the distance here is going to be x, right, which is going to be greater than 0. If we compress the spring by applying a force, then we're going to have x be less than 0. And so the position could be negative or positive depending on the force, the direction of the force. Okay, so now this brings me up to Hooke's law. Now Hooke's law is a law that's developed for springs. So Hooke's law, it says, hey, the force applied to a spring is given by this relationship, this constant and x, which represents the distance from equilibrium. Okay, so this is what we call the spring constant. That depends on the spring, the material, the makeup of the spring, and stuff like that. We're also going to assume that the spring, when we stretch it, isn't going to lose its properties. So this law holds pretty much as long as none of the properties are done. Like, for example, if you take a spring and stretch it too much, it may and probably will lose some of its elasticity, right? You ever do that with a slinky, right? You pull a slinky, one of those metal slinkies, too much, it basically, you ruined it. So, we're assuming that none of that is happening, okay? So the spring constant is always positive, but the distance, as you can see, x can be positive or negative depending on whether it's compression or a stretch. Now, so what we're going to do is, since our integral, right, our integral from a to b of the force applied dx, so basically we're going to use this in our integral to find out the force or the work done on a spring by applying a force to a spring. Okay? And so we'll do an example of that. See you soon.